Hi, I'm Ryan Baker, and this is Big Day in Education. Today we start the second week of our class with a continuation of our discussion of prediction models and classifiers in specific. Today we're going to talk about detector, or classifier in general, confidence. Let's quickly reconsider classification. As you may remember, in classification, there's something you want to predict called the label or the predicted variable, and that something is categorical. Now, it can be useful when you're classifying to know yes or no, to get an answer yes or no to a question. For example, let's say you go to the Ptarmigan's disease detector, and the detector says you don't have Ptarmigan's disease. Now you can throw a big party and be happy. But it's even more useful to know how certain the prediction is. Let's say that the detector says that there's a 50.1% chance that you don't have Ptarmigan's disease. Are you still celebrating? Not once you know the confidence. That's why confidences matter. You can use detector confidences in several ways. First of all, for gradated intervention. Maybe you want to give a strong intervention if the confidence is high, over 60% or 70% or whatever. Maybe you want to give no intervention at all if the confidence is under 40%. And maybe you want to give some sort of fail-soft intervention, an intervention that's just not that harmful if you've given it incorrectly if the confidence is in between. Now, these decisions about the strength of intervention can be made based on a cost-benefit analysis. And you have to ask, what's the cost of an incorrectly applied intervention compared to what's the benefit of a correctly applied intervention? Let's look at an example. Let's say that an incorrectly applied intervention will cost the student 1 minute of time. So there's no cost to learning, it doesn't drive the student away, but the student loses a minute of their time. In each minute, the student is typically going to learn 0.05% of course content. So there's a real cost to losing that time. A correctly applied intervention will result in the student learning 0.03% more course content than they would have learned otherwise. In that case, we can compute the expected value of the intervention based on an equation of 0.03 times confidence minus 0.05 times 1 minus confidence. So in other words, if you're right, you have an expected value of 0.03, but if you're wrong, you have a negative expected value of 0.05. And here we can see this graph plotted on this function plot on the graph. So we can see that if detector confidence is about 62%, then it's good. So let's consider the expected value of the intervention based on these parameters, knowing how good that's going to be if the intervention works, and how bad it's going to be if the intervention doesn't work. And we can actually plot a function on this. And we see that the expected gain comes above 0 when the confidence is about at 61% or so. What if we had a second intervention? This intervention is stronger, but it's also more harmful if it's wrongly applied. So if it's correctly applied, then you're going to get a boost of 0.05, but if it's incorrectly applied, you're going to lose 0.08. In this case, you can see that you can plot a second line, the orange line, and see where the two lines intersect. So what you can say from this is that there's a certain range where the weaker of the two interventions starts to work, where it comes above 0, and it's better than the stronger of the two interventions. That's the fail-soft range. In this case, between about 62% and about 75%. Above 75%, you want to use the stronger intervention. So by doing this type of cost-benefit analysis, you get an idea of where you want to apply interventions. And it isn't always just at 50%. There's this kind of idea, 50% is where you're right. But in fact, you should look at the actual cost and benefit of an intervention when you decide when to use an intervention. 50% is often not the right place to actually make a decision.
Now, there's another way to do this that in fact is a little more popular, which is called cost-sensitive classification. In cost-sensitive classification, you tell the algorithm that false positives and false negatives have a different cost. For example, fitting a model to try to minimize an adjusted RMSE that weights false positives and false negatives differently, rather than just using a flat RMSE. And in this case, you're actually adjusting the predictions themselves rather than your decision thresholds. But it ends up in much the same place of weighting positives and negatives differently, errors in terms of them. And this can be applied to most modern classification algorithms. So a key additional use of detector confidence is in discovery of models analyses. When you use the model in further analysis, you often want to retain all of the information and the uncertainty in the models rather than kind of transforming an uncertain prediction to what looks like a certain one. And also rather than treating a prediction that looks pretty uncertain and a prediction that's very certain like they're the same. We're going to discuss this in detail later in the course. Another interesting issue with confidence that shows up more in classic algorithms than more contemporary ones is lumpiness of confidence. For example, a classic decision tree, might only give you confidence values of 100%, 2/3, 50%, and 2.22%. This isn't a problem per se, but some implementations of standard metrics, like the implementation of AUC-ROC in R, can behave oddly in this case. We'll discuss this later in the week. As I said, it's common in simpler, earlier generation classifiers. You don't see it as much in some of the more contemporary ones. It's almost always a good idea to use confidence when it's available, but a lot of metrics don't use it, and we'll discuss this later this week. Another cool recent development is confidence in your confidence. So a lot of the classic ways of assessing confidence have to do with the model's proportion of cases where it makes where a certain decision is right. But that often can overestimate how certain the model actually is in its confidence. And recent methods make it possible to estimate the variance or standard deviation around a confidence value and a 95% confidence interval around a prediction. It's not widely used as of this writing, but there's a lot of cases where this makes more sense than simply saying 75%. Knowing that the model's prediction has a certain degree of uncertainty, that's very confident about the fact it's 75% confident, or it's really not that confident at all about that estimate, can tell you a lot about what you should use those predictions for. Another thing worth talking about is risk ratios. Risk ratios are a good way of analyzing the impact of specific predictors on your prediction. Risk ratio is used with binary predictors, and the way it's calculated is we take a predictor P, and the risk ratio is the ratio between the probability of some result, like say a negative outcome, when P is 1, over the probability when P is 0. So let me give a concrete example. Let's say that we have a model feature, does the student get into 3 or more fights in school? Well, maybe if students get into 3 or more fights in school, they have a 20% chance of dropping out, but if they don't get into 3 or more fights in school, they have a 5% chance of dropping out. The ratio of 20% to 5% is 4, so the risk ratio for this variable of getting in 3 or more fights is 4, which means, in turn, that students are 4 times more likely to drop out if you get into 3 or more fights in school. Risk ratios are very interpretable, and that's one of the reasons I like them. They're way more interpretable than odds ratios, for example. So you can turn numerical predictors into binary predictors with a threshold, like in our last example, and that can become a clear way to communicate the effects of a variable on your predicted outcome. So thank you very much, and in our next lecture, we'll move on to discussing some diagnostic metrics.